All right. Thank you all for joining us. We're just going to give it a few more seconds for a few more people to join, and then we will get started. All right. Good afternoon, everyone, and thank you for joining us today for our National Jeweler Supplier Spotlight webinar series. Today's webinar is presented by GIA. Before I hand it over to GIA to get the webinar started, I wanted to let our attendees know that if you have any questions, you can type it into the Zoom Q&A box. GIA will answer these questions as they see fit throughout the webinar. Also, today's session is going to be recorded and will be available on the National Jeweler website by this Friday. And I will pass it over to GIA now to get started.
Good morning. Thank you for joining us today for this webinar on natural diamonds. My name is Jim Shigley. I'm here with my colleague, John Kaysen. I created this talk about natural diamonds to perhaps help jewelers speak more effectively in a way about this subject, because I think this is a great but often somewhat untold geology story. And I think this is important today as we're dealing with a lot of advertising related to lab-grown diamonds in the market. So with that, we will begin. This presentation is copyrighted. I'm going to try to give you some ideas that you might consider about natural diamonds. Diamonds are a rare, exceptional gemstone, and one of the most chemically pure minerals, being 99+% carbon. This little diagram in the center just shows the atomic structure of diamond, with the carbon atoms each bonded to 4 neighboring carbon atoms in a 3-dimensional structure. And as this structure is what gives rise to many of diamond's distinctive physical properties and its crystal shape. We're all familiar with the famous De Beers marketing slogan, "Diamond is forever." But I think we should recognize that diamonds are the oldest objects that you will ever hold in your hand. Some diamonds contain mineral inclusions that were trapped from the deep earth. And geologists can age date the time of formation of the diamonds from certain inclusions. This formation age can go back a very long time ago, and I just indicate here at the bottom for the Diavik mine in northern Canada, some of the diamonds have been determined to have been formed 3.6 billion years ago, which is about 3/4 of the age of the Earth. Now, just to kind of get your head around what 3.6 billion years represents, if I divide that number by my age, you get about 48 million human lifetimes. So that's kind of 48 million people lined up in a row. That's kind of the time that we're talking about for diamond formation and very early time in the Earth's history. Well, natural diamonds are formed and preserved deep in the earth. To show you some pictures of diamond crystals, which should look fairly recognizable, familiar to you. Well, the shape of these diamond crystals is one evidence of their long geologic history. And what I'm going to try to talk about today is, in fact, kind of a signature of natural origin. That signature is revealed by the shape of the crystals, by the internal structure features you see under the microscope, or by a fluorescent lamp. It's revealed by trace element impurities that are caught up in the diamond during its formation. It's also revealed by what we call atomic level defects in the structure of the diamond, which we can detect with various scientific techniques. So it's this idea that diamonds have a long geologic history, a geologic signature, which is the principal way of recognizing natural diamonds from lab-grown diamonds, which, of course, formed very recently and very quickly in the laboratory or a factory. Natural diamonds are found in what are referred to as kimberlite or lamproite pipes of volcanic rock, which occur in what the geologists call our cratons, which are very old geologically stable parts of the Earth's crust that are exposed at or near the Earth's surface. And these are indicated by the colored areas of the map on the right side. And these areas are really the target areas for exploration for potential new diamond deposits. Natural diamonds, we now know, form really in two environments in the lower crust or upper mantle of the Earth. Most natural diamonds form in what's called a lithosphere, which is a solid upper crust of the Earth at a depth of about 100 miles and temperatures of about 1,500 degrees centigrade and pressures of about 50,000 bars. And just to kind of relate to what that is, 1 bar is the atmospheric pressure that we experience here at sea level. So most diamonds are forming at about 100 miles down in the lower part of the solid crust. But based on work over the last few years by some of our researchers here at GIA, looking at some of the unusual inclusions in what are called type 2 diamonds, we're now thought to have formed much deeper in the Earth, perhaps 250 to 450 miles below the surface, where you've got higher temperatures and pressures. So it's these two environments that are where diamonds are forming. Carbon is a common element in the Earth, and you've got the high temperatures and pressures, so you've got the right conditions for diamond formation. And then they can be brought to the surface some later point by eruptions of a kimberlite or lamproite magma. I mentioned the idea of a geologic signature. I have this kind of rough timeline on the top with age of the Earth at 4.5 billion years ago and diamond formation at the Diavik mine about 3.6 billion. And then you have a long, long period before the diamonds were actually erupted in kimberlite magmas about 55 million years ago. So you have this extended period of residence time in the mantle once the diamonds form. And they're there at high temperatures and pressures. And during that residence time, you can have further growth of the diamond, you can have dissolution, you can have regrowth. So you get oftentimes kind of a complex internal structure. Nitrogen is the principal impurity element in diamond because the nitrogen and carbon atoms are about the same size. So when diamonds form initially, they incorporate nitrogen frequently, and they incorporate that nitrogen as single atoms. Well, when you have nitrogen in single atoms, you have what's called a type 1b diamond, and those diamonds are yellow in color. But during this long residence time, you can have diffusion. That is, the nitrogen atoms move through the structure and end up being next to each other, which is called aggregation. And now you have a different cause of color. So that ends up, the 1B yellow diamonds are converted over time to 1A colorless diamonds. And finally, you get creation, modification, and destruction of atomic level defects in the structure. All of these things happen during this long period of time in the Earth's mantle. And it's this signature, all these types of features, which distinguish natural diamonds from lab-grown diamonds. Once they're formed and they've been sitting down in the mantle, they were brought back very much more recently in geologic time by rapid eruptions of an explosive magma. On the left-hand picture, I show you a volcano, which you're all familiar with. volcanoes are sitting over magma chambers in the crust of the earth. And that magma occasionally erupts, and you end up having repeated eruptions and forming over time kind of this cone-shaped appearance of a volcano. That's not what's happening for these eruptions of in kimberlite and lamproite magmas. We think these are much more a single type of event. It's an explosive event. It's important to recognize that these eruptions have never been witnessed. They all occurred in the past. But you have this violent eruption bringing diamonds up from deep in the earth, and they erupt out onto the surface. They're thrown up into the air. They're falling onto the ground around the cone. But once at the surface, these volcanic rocks, the kimberlite and lamproite, begin to weather rather quickly, and they decompose. So today, the pipes are often found when you see them out on the landscape in kind of a depressed area of the topography, or in fact, beneath bodies of water. So on the right-hand picture, and I believe this is just a view up in northern Canada, we have the kimberlite pipe, which is only about 500 feet across. And you can see it's kind of in a depressed part of the topography, and part of the pipe is covered by water. But again, the idea is this is a one-time, not a repeated magma event, so you don't have a volcanic cone formed. Well, the host rocks of diamonds, kimberlites, lamproites are both rare. Since 1880, about 7,000 of these pipes have been examined around the world, but only about 60 of them, less than 1%, have had sufficient diamonds to make the mining economically viable. So you have rare kimberlites and even rare diamonds found in them. Loose diamonds were first recovered in India beginning of about 500 BC in the region which has kind of been come to be called the Golconda region, which I've kind of circled with a red circle there on the left-hand map. And the diamonds are found loose at the surface, and they were recovered by washing sediments or panning in the river using very basic tools. India was the major source of diamonds from about 500 BC until about 1700 AD, about 2,200 years. But in the early 1700s, diamonds were found in Brazil, again, loose in the sediments or found within sedimentary rocks, such as this old illustration on the left-hand side. Initially in the state of Minas Gerais, and about 100 years later in the state of Bahia. So from early 1700s, for about the next 150, 60 years, Brazil was the major source of diamonds in the world. Diamonds were found in South Africa. The first one was found in 1867 along the Orange River. The view on the left shows the Vaal River, which stretches out to the left, to the northeast, and the Orange River, which stretches to the the southeast on the right, and they merge and they're going to flow westward or toward where the viewpoint of the viewer, out to the Atlantic Ocean. So when they first found a diamond, some individual walking along the banks of the river found a diamond. It instituted a kind of a land rush to this part of South Africa. And for a couple of years, they were mining along both these rivers. This view is to the east. So the famous town of Kimberley, where the big hole is about 50 miles toward the horizon, straight out from where these two rivers converge. So all the major South Africa kimberlite mines are kind of out in the distance of this field of view looking to the west. This is an old illustration So there at the time they were looking for diamonds along these rivers or loose in the sediments. But they started exploring the area. And in 1871, at a small hill about 40 kilometers south of the Vaal River, they found diamonds in weathered kimberlite. And this is the first time they'd ever found diamonds in the actual rock, which now then gave geologists a much better understanding of what to look for. So this pipe was exposed at the surface, was deeply weathered, and it was divided up into claims, which were, you were working at your claim, which is probably about 30 feet by 30 feet in area, and you're digging down. And so there were hundreds of claims, and eventually these were all bought up by the De Beers Company. And by about 1881, they consolidated all the claims. And that ended up, mining continued there for the next roughly 40 years. And mining by some 50,000 individuals yielded about 13.6 million carats of diamonds, or about 360,000 carats per year. I visited this place. I was in South Africa in 1992, and the entire production of 43 years would fill these 3 mine cars, which are shown there on the right. I think these are just pieces of glass, but it gives you some idea of the work of all these individuals yielded this many diamonds. And they dug this pit. This is the largest open pit that's ever been dug by hand, about 1,500 feet wide, 800 feet deep, and now partially filled with not rainwater, but groundwater, which you see there in the center. There's probably about 20 some countries where diamonds are found today, but the major producers are Angola, Botswana, Canada, Russia, and South Africa. The average production of all the mines throughout the world is roughly about 140 million carats per year. Well, if you had all those diamonds, those 140 million carats of diamonds, and you formed them into a cube, the cube would be about 6.5 feet on a side. So this gives you some sense of all the work that goes into producing these diamonds, which doesn't really fill a large volume. And just to kind of emphasize that, this little cube on the left-hand side represents 1 ton of kimberlite, about 2,204 pounds. It's about 30 inches on a side. And the grade of diamonds in that 1 ton would be perhaps 1/100th of a carat, maybe up to 1 carat. But there's a huge amount of rock has to be moved for a very small amount of diamonds being recovered. And I just tried to illustrate that on the right, showing you an exercise ball on the left. The annual world production from all the mines of 1 carat diamond crystals would fill that exercise ball, while the production of 5+ carat crystals over the year from all the mines would fill a basketball. And I just want to kind of emphasize how rare these actually are to be found today. This is a picture of the Diavik mine the Ekati mine in northern Canada. It's a remote location. The closest town is about 200 miles away. You can see this is flat terrain. The glaciers came through and kind of ground away everything. There is nothing in this location. So when you're going to build a mine, you have to go through an extensive exploration to find this location. And then you have to bring everything you need to do the mining: the tools, the equipment, the vehicles, the structures, the processing plant. And you have to build all this in the middle of nothing. I estimated the size of this mine footprint would be about 5 miles on a side, roughly. So that's 25 square miles out of a country size of Canada of 3.8 million square miles. So this diamond mining is often sometimes portrayed as kind of being quite damaging to the environment. I don't think that's really quite accurate when you consider the small area of the mine in a huge area of land, oftentimes in very remote parts of the world. So diamond mining is kind of accomplished initially from the open pit, and they're going to kind of dig down or bring vehicles down to the bottom, and they're going to load up all the debris in the pit or what they are blasting, and those are trucked out or hauled out by some conveyor system. But eventually the decision oftentimes is made to go underground, and so they would dig a vertical shaft down and then horizontal tunnels that you're going to intersect at various levels in the pipe. And then when you get those driven through the pipe, you're going to have explosive charges that you put in the roof of the solid kimberlite, and you blast. The kimberlite is broken, falls down into the tunnel, and is removed and brought to the surface. About 85% of the world's natural diamonds by volume and 50% by value are produced and marketed by large-scale mining companies, which together support the livelihoods of about more than 10 million people in the diamond pipeline. As I said, I had a tour of many of the diamond mines in South Africa by De Beers in 1992. One of the places I visited was the Cullinan mine, which has been operating for almost a little more than 100 years. The processing plant is shown in the front and the open pit is shown in the back. This is the area where the famous large Cullinan diamond, 3,000 plus carats, was found in 1905. Well, I had a tour of the entire plant and also of the open pit. And I was in the open pit with the mine geologist, the senior geologist. And I asked him the question, do you ever see a diamond in the mine? And he said, no. We only see them at the final stage of the ore processing. And that was kind of an incredible idea to me, that you would be working all your life digging and moving rock, but you actually never see the diamonds in the mine. It's still kind of an amazing idea. And again, it just reflects the rarity of diamonds in the host rock. This is the inside of the processing plant at the Diavik mine. The ore processing involves a couple of steps. So once you get the kimberlite ore out of the ground, you're going to crush it. And they have kind of various sizes of the rock that they want to crush it down to. You're going to wash all the way the fine particles, and you're going to screen the rock fragments by size. And then you're going to run that through some kind of a heavy medium separation to separate all the diamonds and all the heavy minerals. And then you're going to recover the diamonds from that concentrate by a couple of methods. You can have the diamonds go by on a table, a moving table, and you're going to pick them out by hand. You can run that concentrate over a grease table. The diamonds are attracted to grease and everything else flows off by water. And then they also have a fluorescence technique where they run the concentrate under a strong fluorescent lamp, and the diamonds fluoresce. And there's a optical detector, and when it spots one of these crystals fluorescing, there's an air jet that's used to pop the diamond off into a recovery bin. Well, these are the largest diamond mines in the world by provable reserves, kind of listed in the order of their importance. The ones that I've listed with the double asterisk and a couple others shown at the bottom, I've visited. First thing you might notice is that 5 of the top 10 are in Russia, in Siberia, most of them. And this is why the sanctioning of Russian diamonds is having such an effect on the whole diamond trade. I've also tried to kind of indicate to you, diamond mines have kind of a lifetime, roughly of about 30 years, at which time they end up, the cost to mine the diamonds doesn't cover the cost of the mining. So the mining, oftentimes the mine is closed. Well, looking at the company websites of these mines, I tried to indicate roughly the approximate closing year. And you look, it's in the next 10, 15, 20 years. That many of the major mines are open, are going to be closing likely. I mean, closing as an economic decision. But I think that means that there needs to be a continued worldwide exploration effort to find new localities, because the ones that the jewelry industry is dependent on, again, in not too many decades in the future, were likely, many of them will be closed. The most recent example of a mine closing is the Argyle mine in Northern Australia, which after 37 years of operation, closed in late 2020 after producing 865 million carats of diamonds, of which these pink and red diamonds were certainly the most well-known. But when a mine closes, the expenses don't stop. In most mines in most countries today, when the mining ends, the mining company has to put everything back. You've got a 3 to 5 year program of putting everything back, 3 or 5 years of work and expenses to close the pit and fill the underground workings, to remove all the waste dumps of ore, remove all the equipment and infrastructure, restore the land and return it to its traditional custodians and support its future use. And you've got to continue to monitoring the environment. So there's a huge effort to kind of restore these mining locations at any major mining site. So we're now we're going to be faced with some exploration uncertainties. How do you locate a new mine? How do you discover a new occurrence at those craton portions of the world I mentioned earlier? Is the pipe accessible for evaluation, or is it buried under several hundred feet of sand, for example? Does the pipe contain diamonds? Does it contain gem diamonds? Even if you had diamonds, can you legally and economically mine at this location? And is the recovered diamonds going to support your mining costs? And what's the estimation of the future total ore reserves? These are all really important questions that a mining company has to deal with in trying to find and bring a new mine online. This is a map of South Africa, and the tan area is kind of the watershed or runoff going into the Orange River and the Vaal River. River is the ones I showed you on the photo a few slides ago. So right there in the center where the two rivers come together is where that photo was taken. The red dots on the map indicate the location of kimberlite pipes. So all these pipes over geologic time were weathering away. The diamonds were released in the environment, and over time by erosion, ended up, many of them, in these rivers. And they were then transported westward about 450 miles to the Atlantic Ocean. And they were dumped in the bottom of the Atlantic Ocean. And they were carried north by the current and ended up being washed up on the beach in Namibia, kind of in that area of the yellow box on the left-hand side. So diamond mining is done beneath the ocean today. mainly by a consortium of De Beers and the government of Namibia. And they have some mining ships, and the whole processing plant is on the ship. And the ship goes out and is going to anchor over a spot in the ocean, and they kind of locate themselves and position themselves. And then they have a remote control vehicle that goes down from the ship and is going to be suctioning the bottom of the ocean, all the sediments and as well as the diamonds. So they're recovered, and then this sediment is going to be brought up to the surface of the ship, and the diamonds are recovered out of that sediment. And this has been an important activity because a lot of these diamonds that survived this 450-mile trip down the Orange River are the best quality diamonds, because the poor quality ones tend to be broken up by just the getting bumped along in the river. The diamonds are also recovered today along the coast of Namibia. This is a restricted zone called the Spargabate, about 200 miles north-south and 60 miles wide, that you cannot get into. And this is a big sand moving operation in order to expose the bedrock, which is shown there on the right-hand side. This is the natural bedrock beneath the sand dunes, and the bedrock contains gullies. And so once this bedrock is exposed, they have workers come in and they're going to be suctioning all the material in these gullies. And again, that's put through a processing plant to recover the diamonds. Well, there's also artisanal diamond mining that's done in many parts of the world, principally in Africa and Brazil, and I think it's the main areas. Although the production represents only about 15% of the total diamond supply. Millions of people, men and women, are employed in artisanal mining of diamonds and other gemstones across parts of the world. Well, this is where some of the problems in the industry begin, because the various challenges facing these artisanal miners: unsafe working conditions, child labor, human rights violations, limited income, and oftentimes, unfortunately, they tend to be exploited by the people who come to buy the diamonds and don't really give them a fair price. I'd like to kind of finish my part in the next few minutes talking a little bit about diamond origin determination. I think many people in the trade are familiar with origin reports on colored stones, important colored stones like ruby and emerald and sapphire, for example. And the question is, can we tell where diamonds come from? Well, I show here on the left a piece of kimberlite, which is commonly thought of as the host rock. And on the left, a piece of conglomerate, which is a sedimentary host rock. Well, diamonds didn't form in either of these rocks. They don't form in the kimberlites. They don't form in the rivers. The kimberlites and the rivers only transported them from where they originally were formed to where they're found today. And both these environments move diamonds relatively so quickly that they don't really impart any characteristic geographic or country signature about where the diamonds originated. So I started a few minutes ago telling you the diamonds form in the mantle. That's where they originate, but they're found today in various countries around the world, but we cannot tell what country they came from because they have no signature of that country. They have the signature of the mantle environment. So, kimberlite pipe exposed in Brazil under some 20 feet or so of sediment. The kimberlite, the weathered kimberlite, is the gray, the greenish brownish material. In the center of the photo, That's dug up and put in a pan and washed. And then they come and the heavy minerals sink to the bottom of the screen. And they flip the screen over, and you see some examples there in the front where the reddish and blackish heavy minerals are at the bottom of the screen, but now at the top of the pile. And that's where the diamonds would be found. But kimberlites are kind of like elevators. The elevator picture at the bottom, picking up passengers, picking up diamonds at various spots as they're traveling upward through the mantle to the surface. Whereas the river is transporting the diamonds along the surface. So it's kind of in a way, kind of like a school bus. You're picking up diamonds at various parts and transporting them downriver and dumping them somewhere else. So the kimberlite and the river are just the transporting agents, not where they originated from. So we think today that the diamonds are brought to the surface by these eruptions of these kimberlite magmas, maybe from depths of 100 miles or more. And it's likely that the diamonds pass through various source regions in the deep earth, and all those diamonds get caught up and are brought up to the surface rapidly. Geologists now think that the ascent of this kimberlite is so rapid that it may only take a few days for the magma to come up from deep in the earth. It's kind of under pressure, and as you get closer to the surface, that pressure decreases, so it's kind of like opening a soda bottle, and that's what blasts the diamonds out on the surface. But the idea is there is a signature in the diamond, but it's the mantle environment, not the country where the diamonds are found today. Well, rough diamonds certainly vary in their size, shape, color, transparency, quality. And diamonds from a single mine sometimes may display distinctive features. The shape, the appearance of the diamond, rough diamonds. But when they're mixed together from different sources, these features become much less apparent. And of course, these surface features are removed during manufacturing. So they're of no help for what we would call diamond origin determination. So based on our understanding today, it's not scientifically possible for us to tell where a polished diamond comes from. And I don't think there's any technology, analytical technique on the horizon that's going to solve that problem. We've been grading diamonds here at GI since 1955. Diamonds form in more similar geologic environments in the earth. And their market value when polished is depending on the quality factors, the 4 C's, color, clarity, and so on. You get high quality diamonds from any mine. So there's no indication of a geologic source influencing, the value of a polished diamond, because you get high quality diamonds from everywhere. And there's some significant challenges to origin determination if you were going to try to conduct a study. From what we know, after looking at millions of polished diamonds over the last 60, 70 years for grading, there are no diagnostic visual features to tell where a diamond comes from when it's a cut stone. Secondly, there are no collections of diamonds from all the major mines around the world that would be available for scientific study. And that study would be expensive and destructive to some of the diamonds. Trace elements are a possibility, but they are so low in concentration that analysis is quite difficult. So we have no scientific evidence that we can tell where diamonds come from. And occasionally there might be some article that we've seen a couple of them that suggests that maybe a geographic origin is possible. But in reading the article, they seem to have too few localities represented and too few diamonds studied to really support their conclusion. So I would just like to summarize and emphasize that there is no geographic signature of diamonds that we would need to have an origin determination. So what we do, we have kind of an alternative. We call it an origin report, but it really is a matching report. So what we have are mining companies that are partnering with us, and they supply a rough diamond, such as the upper left side of the top picture. And we're going to characterize that rough diamond. All the ways that we have of characterizing diamonds, visually, fluorescence, spectra, all the features we can look for. We return the diamond to the mining company. It's going to go through a stage of cutting, and then they end up with a final polished stone on the right. And they send that back to us. And they say, we certify that this polished stone came from this rough diamond. And then we're going to document the polished stone to be able to see if we can determine with some high degree of evidence that it is in fact cut from that rough stone. So in this case, origin is preserved more as a fact. It's based on factual observations, not just kind of inferred where we think this diamond based on the inclusions may have come from some source. So it's kind of much more like a chain of custody from a known source to a rough diamond to a polished diamond. And since the last couple of years, we've issued about 90,000 of these origin reports with about a 90% success rate. What happens to the other 10%? There just weren't enough features in the diamond where we could positively match it with a rough crystal from which it was allegedly cut. So with that, I'm going to introduce my colleague, John Kaysen, to finish up the presentation. Thanks, John.
Thank you so much, Dr. Shigley. Very informative and interesting as usual. We're going to sort of move into now, look at some natural rough diamonds in the microscope. But before we do that, we're just going to touch a little bit on cutting and just introduce the concept and what the industry refers to as manufacturing diamonds. That's kind of cutting. So we're kind of alluding to the rarity of these of natural diamonds. Cutters, have to save every part as much of the diamond as they can. They're trying to maximize their profits by retaining as much of the diamond as they can. And thinking about the 4 C's when they do this, they paid for the rough diamond based on its size and quality in terms of color and clarity. They then need to kind of retain that and maximize. So planning is really, really important. I was just reading the other day that the Lesotho Promise, which was found in Lesotho by Graf Diamonds back in 2006, they spent about a year planning and cutting that diamond rough, that 603 carat rough, to make sure they maximize the value out of it. So cutters and planners are highly experienced, of course, and understanding how to get the most out of their rough. Nowadays, though, we have a lot of technology involved here where we have rough diamond mapping and computer-aided design where they can really maximize, minimizing the inclusions that are in the stones, maximizing the sizes of the stones, and really, really gaining the best value they can. Now, understanding diamond rough is kind of important as well. So looking here on the top left, we have a picture of a natural diamond rough, and this is its kind of ideal habit. It's an octahedron shape. It's kind of like a pyramid on top of a pyramid, but it's one unit. And this is how diamond will form in its ideal state in the earth. Now, in this stone, we know there are areas of what we call crystal planes. So these are areas of different weaknesses or strengths due to the arrangement of the atoms in the stone. So we're looking here, we have this cubic plane here, the blue cubic plane. Let me point to this for you guys in the picture. So this plane here is actually an area where we learned over many, many years, I say we, not GA, but cutters learned that this is the best direction to cut or physically saw mechanically a diamond through this direction here. And back in the 1600s, diamonds could be sawn, and they were sawn with using either brass or iron wire coated in olive oil and diamond grit to slowly saw through, which obviously took a long time, I'm sure. Another way we could actually break off or cleave a diamond here. So these octahedral planes, there are 4 of these in a diamond. So a diamond has 4 cleavage directions. And if a diamond is hit parallel to this plane, you can actually cleave the diamond at the atomic level and a whole slice of diamond will slide off. Of course, you need to be extremely careful when you're doing that. And then the octahedral plane here, there's 12 of these. Dodecahedral planes. There's 12 of these here. So we have 1, 2, 3, 4 running around the stone here. Then we would have 1, 2, 3, 4 there, and then 4 on the other triangle edges. Now, we look at this dodeca, that's from Greek, that's 12, and hedral means face. So that's 12 faces, and then octahedral will be octa, 8, and hedral faces, 8 faces. So cutters understand how they interact with these planes within the diamond to cut or fashion without breaking the stones or chipping, because diamonds are extremely hard, but they can be broken. This image here shows, what we might do to get the maximum size diamond we want out of our stone. And if you look at the diameter here of this stone, we want to retain the largest average girdle diameter we can, because when people buy diamonds, generally we'd like to buy diamonds that are as large as possible, that fit our budget. And by following this square cross section here as much as possible, they get the largest stone. Of course, they have to figure out the angles they require and proportions to make sure the diamond interacts with light correctly, which we of course know a lot about with our cut grade technology. So they could also cut slightly differently here. You look at this stone here, they cut a smaller diamond on the top. So how they position this is going to depend on the size of the rough and magic sizes we think about. We might want this stone here to at least meet a carat or larger. If it was under that, we might not be able to cut this stone here, because once we get under a carat, we know our price per carat drops. So that would be one example of one magic size. Anyway, moving on here. Here's some images of some cleaving. So this is the way we would cleave a diamond on the octahedral, parallel to the octahedral plane, by cutting what we call a kerf in the diamonds to position this blade, and then hitting the blade hard, and you would end up hopefully cleaving this piece that you wanted to remove off the stone. Sawing was something that came about, mechanical sawing with a blade like this came about in the very, very early sort of 1900s. A Belgian immigrant into the US came up with this technology of this thin blade and coated with diamond powder or diamond grit to cut through the diamond. And this, again, you want to try and cut this on that cubic direction if possible. Of course, nowadays we can use lasers. And lasers really negate the need for worrying about which direction we cut this stone, because lasers aren't really mechanically cutting the stone. They're burning it or sort of melting it. So they can cut from any direction. Bruting was something that was invented around the 1870s. And this is where we first started to see round circular outlines of our diamonds. Before that, they weren't round because we couldn't create that round shape. Essentially, this is just spinning one diamond against another, and slowly, as they rub against each other in this spinning motion, will actually create the round outline. Early machines were powered by steam until later on when electricity came into play. Of course, again, talking about lasers, we can use lasers now. So lasers very efficiently will cut outlines of diamonds, and of course could cut different shapes as well. So when we cut a diamond, the first stage really is blocking. So the very, very important stage, because we need to make sure that our proportions and angles are as best as possible to make sure that we get the ultimate light return from our stone. So blocking, we have 8 bezel facets on the crown. There will be 8 pavilion facets on the pavilion of the stone, and then a table and possibly a cooler. So this sets up our diamond, really. This sets up the shape. It can't really be changed after this. It's an extremely important stage. After the blocking, we'll go into polishing, and I'll just kind of show you a kind of quick schematic here of if we had an ideal habit rough diamond, we would start off with this shape. We would saw, we can brute, create the round outline, we can block, and then we add the upper halves, lower halves, star facets, and we end up with our what we call the brillianteer in the polishing stage of our stone. So on that note now, let's look at some rough, and now we can kind of look and see how some examples of how the cutters tried to save some weight. So I'm going to turn my camera on over here. And I already have a octahedral diamond in the microscope here. And I'm just going to magnify my window a little bit so I can see what I'm looking at here. Because I can't see directly in the microscope myself. So, okay, so this is an octahedral diamond here. So if you look, we already talked about the faces we might see here. So if I bring my pointer probe in here, on here we have our dodecahedral faces here, and we have these parallel lines on these faces. So in a stone like this, it's easy to kind of know where they are. But on a rough that's far less organized in shape than this, far more irregular, which they can be, diamonds, like I said, this is the ideal habit. De Beers had over 16,000 categories of rough diamond that they would use to qualify the value of their stones. So, you know, we can see that this is really the ideal. And as I tip this is kind of fun. We can see some growth marks on this octahedral face here. Let's bring this into focus here. And do you see those triangles on there? These are called trigons. I'm going to zoom in a little bit more. And these little trigons here, these are growth marks. And we find these on our octahedral faces. So if the diamond was not in this ideal crystal habit and was far more irregular, if we saw these triangles on any part of the stone, we would know now we're looking perpendicular to that octahedral face. So that would help us when we wanted to maybe cleave the stone. So there's our rough there. So now, as we talked about in the diagrams in the PowerPoint earlier, what the cutter's really ideally trying to do is when we look in cross section here, they want to make sure that their diameter of their stone really takes up as much of this as possible. So you notice if there were any areas that were missing here, they really want to kind of keep this as large as they possibly can, because that is where all the weight in our diamond is going to be once it's cut. So then let's look at a stone that's slightly less regular than what we just looked at, piece of rough. And I'm going to zoom in. So you see this is far more irregular looking than the stone we just looked at. So how do I figure out where my faces are on this stone? So if I zoom in here, I can actually see, let me move this up a little bit. And I'm using reflected light here to look on the surface of the stone rather than inside the stone. I'm going to zoom up and then I'm going to keep still. Okay, I'm in a stone holder here. Now, do you see those square depressions in the stone here on the kind of right-hand side around 3 o'clock? We're going to move the stone a little more. So these square depressions indicate our cubic face of our diamond. So right now, when I look at here we go, that's a little bit better. Let me just let go so we can steady this, because high magnification, any little shake of my hand makes it less clear. So these cubic depressions here indicate we're looking perpendicular to the cubic face. If I wanted to saw through this stone, I would know which direction to saw with the most efficiency. Now here, we have what we call a mackle. So this is diamond rough. Now notice there's a kind of a triangular shape here. Now, this stone actually twinned, so it's not the nice octahedral shape, excuse me, that we would like to see. It's been twinned. So when the diamond twinned in the earth during its growth or regrowth, it kind of becomes much flatter looking. So when I tip it to the side here, you'll see it's quite flat. And what happened is it twinned along a specific atomic plane, so, or twinning plane, we actually would call it. So it's almost like you could say it was growing and then it sort of stopped growing. And when it started growing again, the atoms were lined up in a slightly different direction and started growing again. And what we have here is we can see, my kind of stone hole's a little bit in the way here, but I'm going to point here with my pointer. You see there's a line running through the stone here. That's the twinning plane. And you notice that there's diagonal line coming down here from the top to this direction, moving out slightly to the right, and then from the middle here, the diagonal line's moving from kind of the center here out to the left. So this is two different directions of growth. These are actual octahedral planes that are running in opposite directions. So it would be really trying to challenge into, you couldn't cleave this because you want to cleave a long parallel to an octahedral plane, but then the plane's running this way in the top part of this stone, but in the bottom part's running the other way. So this would be challenging. One thing that mackles are used for quite a bit in the industry is fancy cut stones, or fancy shapes, because they tend to be shallower than round brilliants. And if you look at this, this would be a fantastic trillion or triangular shaped stone, because we could retain a lot of the rough from this. Now notice here, when I zoom up, we should be able to see a number of different growth marks on here. There we go. So I see some little trigons down there. I'm just going to try and hold this still and zoom up a little bit here. So there you can see some trigons on there. So we know that's an octahedral face. So there's a mackel. Now, how does that translate when we're cutting a stone? So we think about the first stone we looked at, the first octahedral rough, and I said they would like to try and maintain the maximum diameter out of the stone. So when I look at this stone here, let's just position this so we can see the whole stone. You'll notice it's very slight flat spot on the top of the diamond here. So when we look at diamonds, we measure them in multiple directions to figure out their average girdle diameter, and they're generally not completely round. So there's a very slight flat spot on here. So when I tip this stone over, what we'll notice here is, so I get into position for you all to see, there's what we call a natural on the back. There's a big triangular shape here on the back of the stone. So come in and point at this here. Lost my pointer probe, come back. Oh, here we go. So here's the pointer. So here's this triangular shape on the back of the stone. So it's kind of interrupting the pavilion main facets. Actually, it's interrupting the two lower halves here. So what this is this is actually this original surface of the diamond crystal itself. The cutter didn't cut this, they left this. And it's pretty clever cutting because they left it underneath the girdle. And it really didn't change the outline that much because you can see there's still a small bit of the girdle there. So they're maximizing the average girdle diameter of this stone to retain as much weight as they can. And if I rotate the stone all the way over here to the opposite side, and you'll often find naturals on the opposite side. So this is really interesting of how well they utilize the retention of weight here. Now, if I look at this one here, there's another natural on the other side. And in this natural, I see some growth marks in there. I see some trigons. Now, naturals have very little impact generally on clarity because they're usually under the girdle. It's a natural feature for the stone. Now, they can have a greater impact when they become indented and become more visible from the crown. So here, this next diamond, this is the last time we're going to look at it, and I'm going to have to wrap up because we're running out of time a little bit here. The outline changed quite a bit on this. We look at the top left, just around 11 o'clock. The outline's not quite round at all. When I tip this diamond over, this stone would have had indented naturals. So these are naturals where the diamond's crystal would have actually kind of curved, concaved inwards slightly, if you like. So they could have removed this, but they would have reduced the average girdle diameter quite significantly, which would have reduced the size of the diamond looking from the crown. It reduces the weight quite significantly. But actually, if you look at this and you're kind of a gem nerd like I am, I look at this and think, wow, isn't that cool? They've got all these trigons on the bottom here, these triangular shapes. These trigons were in contact with the mantle of the Earth, potentially billions of years ago. And there they are. I'm trying to keep this steady for you. Let's focus in here. And there's our trigons. So that's really how cutters have been working for centuries, really, really hard to retain the weight of the rough because it has so much value and it's so rare. So on that note, I will move our new Gemolite, GIA Gemolite NXT microscope out of the way. I'll come back here. I'll invite Dr. Shigley back over, if that would be okay, Dr. Shigley. And we will answer any questions if anybody has any questions. Let me see if I can look in the chat here. We have about just under a couple of minutes left. If anyone has any questions. If not, I don't see anything in the chat here. Let's make sure I'm looking at the right chat. Let's see participants chat. Well, I don't see anything in the chat, so I'm hoping that that means that Dr. Shigley was extremely clear with everything explained this afternoon, and myself as well. I'd like to thank you very much for taking some time out of your day to listen to our presentation today, and wish you all a good rest of your day. Thank you very much from myself and Dr. Shigley.
Thank you.